Swayam Prabha. Digital India. Educated India.
Hello, welcome to lecture 32. This is a continuation of the skin stringer idealization problem that we were talking in the last two lectures. So, in this lecture we will be solving certain examples to understand or get a grip on the theory that we have discussed till now. So, in the last two lectures we have seen how to idealize an thin walled aircraft component consists of skin and reinforcement like stringers, spars or longeron using boom and skin in a idealized cross section. So, this is such an example where we have a box like a rectangular box like aircraft component which has a thin thickness T of 0.05 millimeter, and this thickness is uniform across the entire cross section. There are 4 stringers 1, 2, 3 and 4 located at the 4 corners of the rectangle. The area of the top 2 stringers, that is 1 and 2, is given as 0.5 millimeter square, whereas the area of the bottom 2 stringers, that is 3 and 4, are 0.75 millimeter square. The dimension of the rectangular component is given. It is 48 millimeter in the horizontal direction and 8 millimeter in the vertical direction. So, the first problem is to idealize this cross section using the skin stringer framework. And the second part of the problem is that after we idealize the cross section, we have to find out the normal stress at location 1 in the skin stringer configuration. So, let us start and solve this problem. So, as we know that when we try to form the idealized cross section of a given component or part of an aircraft, we consider that the skin thickness is 0 or the thickness of the skin is neglected and the entire area is concentrated at the booms, which are concentrated areas at their locations. So, and also we know that the booms are usually placed at locations where there are stringer. So, here we have stringer at all the corner points. So, we are going to, as per the convention, we are going to place booms at all these corners. So, let the area of boom at 1 be B1, the area of boom at 2 is B2, this is B3 and this is B4. Let me draw the XY axis. This is the X axis and this is the Y axis. Now, if we note, since the area of the top 2 stringers are different from the areas of the bottom 2 stringer, there would be an asymmetry in the cross section about the X axis. So, the centroid C will not be exactly at the center, and let YC from the top flange be the y coordinate of the centroid C. Now, So this is therefore the skin stringer idealized cross section. Now we can see that I forgot to mention another information given in the problem is that the mx is given as 5 into 10 to the power 6 Newton millimeter, and my is given as, sorry, this is 5, sorry, let me write this completely. So, this is 5 followed by 5 zeros, and this is 1 followed by 5 zeros Newton meter. Now, since mx is greater than my considerably, then mx is going to be the predominant moment. So, I will try to make the Ixx of the idealized or approximated cross section to be as close as the actual Ixx of the cross section. Now, we have already made this assumption in the earlier theory that we have discussed. Now, using the same theory, let us try to find out the area of B1. So, the area of B1, as we know, is going to be the area of the stringer at 1 plus 1/6 of the area of web, which is in this case 1/3, plus half of area of flange, adjoining flange, which in this case is 1/2. Now, if we calculate this, this is going to be 0.5 plus 1/6 into 8 into 0.05 plus half into 48 into 0.05. So, if we calculate this, we will see that B1 turns out to be 1.767 millimeter square. Now, B1 is again equal to B2 because B1 and B2 are symmetric. So, I don't need to find out B2 separately. So, B2 is going to be also 1.767 millimeter square. Now, let us find out what is B3. Now, B3 is again going to be area of the stringer at 3 plus 1/6 of the vertical wave that is 3/1 plus half of the adjacent horizontal flange, which is 3/4. Now, if we substitute the value, the stringer at 3 is 0.75 millimeter square, and then we have 1/6 of 3/1, which is 8 into 0.05 plus half of 3/4, which is 48 into 0.05, and that turns out to be 2.017 millimeter square, which again because of symmetry is going to be equal to B4. Therefore, the first part of the problem is solved. We have idealized the cross section, we have found out the area of the 4 booms. So, that was the first part of the portion. Now, let us move on to the next part. So, let me just carry over the figure. So, this is B1, this is B2, this is B3 and this is B4. This is my x axis, this is y axis, this is the centroid 3 and this is YC. And this length is 48 mm. This length is 8 mm. We have found B1 is equal to B2 is equal to 1.767 and the second point is B3 is equal to B4, which is 2.017 millimeter square. So, this is what we have figured out. Now, let us move on to the next part of the problem. The next part of the problem is to find out the direct stress or normal stress at the point 1. So, mx is given as 500 kilonewton millimeter and my is given as 100 kilonewton millimeter. Now, to find out sigma z, we have to use this expression that my, the old expression that we have used earlier, so this is the expression that we have been using. Now, since this cross section has a symmetry about y axis, I x y is going to be equal to 0. So, this is going to be gone, this is going to be gone and this is going to be gone. Therefore, if we simplify this, we are going to have my into y by Iyy plus mx into, sorry, this is going to be x plus so this is going to be the sigma z due to symmetry. Now, we need to evaluate therefore what is Ixx and what is Iyy. Now, before we can find out the sectional property, we need to find out the location of the centroid YC. Now, YC, if we measure about the top flange, is going to be 2 into B3 plus B4, that is 2 into B3 into 8 by 2 into B1 plus B3. That is going to be 2 into 2.017 into 8 by 2 into 2.017 plus 1.767. If we calculate this, this will be 4.26 millimeter. Therefore, YC that we have written here is going to be 4.26 millimeter from the top flange. Now, once we have found this out, we can find out Ixx. Ixx is going to be 2 into B1 into 4.26 whole square plus 2 into B3 into 8 minus 4.26 whole square. So, this is going to be the so let me substitute this. So, this is 2 into so, this is going to be the Ixx. Now, similarly, Iyy can be found out as 2 into B1 into 24 square plus 2 into B3 into 24 square. So, it is going to be 2 into 1.767 . So, that eventually gives Iyy to be equal to 4359 millimeter 4. So, this is going to be the other sectional property. Now, when I have found out the sectional property, I am going to use equation 1 and find out the sigma z at B1. So, the sigma z at B1 is going to be 100, my is 100 into 10 to the power 3 by 4359 Iyy, and x is going to be minus 24 plus 500 into 10 to the power 3 by Ixx, which is 120.8 into y is going to be 4.26. So, this therefore is going to give us the solution for sigma z at B1. So, we can find out the shear, the direct stress or normal stress sigma z. Z is the lengthwise axis using the concept of this is of course, as we have discussed in detail earlier, this is just an approximation of the actual stress at P1, but a reasonable approximation. So, therefore, by using the Skin-Stringer idealization, we can get a rough estimate of the direct stress at the location B1. Similarly, we can find out the stress at B2, B3 and B4 for the applied moment Mx and My. So, let us now move on to a next problem. So, that would be Skin-Stringer idealization of a slanted cross section. So, often the aircraft component, so the last example was a very simplified example where we had a nice regular rectangular cross section. But as you are aware, many of the aircraft component are not that simple rectangular symmetric cross section. We often encounter an aerofoil kind of shape. Many of the aircraft component has this aerofoil shape. Now, it is very difficult to approximate an aerofoil by a straight rectangular cross section. So, for that purpose, we can get a fair approximation of the aerofoil shape by a slanted trapezoidal kind of approximation. So, this therefore is going to be a simpler approximation of the aerofoil shape. So, let us now try to see how to approximate. So, this is a 2 cell. So, I have a slanted 2 cell cross section. There could be stringers at certain location which we can actually replace by booms wherever there are stringers. Or an intermediate approximation would be this. So, this is the actual, then the intermediate approximation would be this. So, an intermediate approximation would be this, and this would be the final Skin-Stringer idealization. So, from here we will move on to here, and from here we will move on to here. So, for this particular case, we need to know how to approximate a slanted portion. So, all this while we have talked about either pure horizontal portion or pure vertical portion, and we have not encountered this slanted position. So, we now have to understand how to model this slanted position. So, let me enlarge this blue colored circle portion and see how the stress is going to be distributed in that section. So, let this this is just this section. I have just enlarged this section. So, now let this thick width be B. Let us take a width of B, and let the thickness be T. Now, since this portion, this blue colored circled portion is slanted, the direct stress distribution is not going to be uniform, rather it will have a linearly varying distribution. So, I will have sigma 2 here. So, let me call it as 0.1 and let us call it as 0.2. So, let us say that the stress here is sigma 2 and the stress here is sigma 1. Now, if I want to idealize this cross section, this portion is going to be replaced by a thickness less skin and two booms B1 and B2. So, we will have B1 and we will have B2. This is, let us call as 0.1, this let us call as 0.2. So, there would be a concentrated stress which I can call at sigma 1 bar, and I can call this as sigma 2 and sigma 1. And now, we have to equate this sigma 1. So, this is the idealized cross portion, of the entire cross section. So, this 2 needs to be equivalent, and we need to find out what would be the area B1 and B2 such that we have the same stress distribution sigma 1 and sigma 2. We will carry on this discussion in the next lecture. Thank you.